Hello. This 7th video will talk us through the dependence of cell potential on concentration. Thus far, we've only looked at standard state conditions, ideally emphasizing 1 molar solutions. So what if we're not at 1 molar? Well, we simply apply Le Chatelier's principle. Let's look at a specific example. If we look at solid aluminum oxidizing to the aluminum ion and the manganese plus 2 ion reducing to solid manganese, that with the manganese plus 2 ion in a 1 molar concentration and the aluminum ion plus 3 at a 1 molar concentration gives us this E naught of 0.48 volts. Well, what if we would change their concentrations? How would the EMF respond? Well, if we look at the first situation, here we're creating a situation where we have a greater concentration of the aluminum as compared to the manganese ion. So, Le Chatelier's principle would say we have too much product than we normally should have if we're referencing the standard state voltage. So, this reveals the push for electrons or the pull for electrons. Well, we have too high of a concentration of our product, so it's not going to be as great of a pull. So we would absolutely expect then the E of the cell, which is not at standard state, to be less than the E of the cell at standard state, 1 molar, 1 molar. What if the concentration of the manganese ion was greater than the 1 molar aluminum standard state ion? Well, here we have too much reactant, if you will. Again, this voltage shows us the push or the pull for electrons. The push by the species that is being oxidized, by being reduced, and the pull by the species that's being reduced, the pull for by the reduction, and the push by the oxidation species. Here, too much reactant, so that is going to cause a greater push. So that would have us predict that the E of our cell would be greater than standard state conditions. When we actually measure these situations, we find these to be absolutely true. So then we know that cell potentials must depend on concentration. Oh, well, could we somehow take advantage of that? Could we use a concentration difference to move electrons? Could we simply, for example, have a situation with 2 solutions of the silver ion, with them being of different concentrations? Now we know that the silver ion can take on an electron to become neutral silver, and neutral silver can give away an electron to become the silver ion. So if we would put a piece of silver as an electrode, of course have our salt bridge, and put these into contact, we actually do get a voltage. When these are in contact, not that they can sense that they are out of concentration, but that's almost the behavior that occurs. So which will go through oxidation, which will go through reduction. What they are going to do is try to reach both the same concentration. Here, this solution is at a lesser ion concentration, so we need to increase the silver ion concentration. Well, what will do that? Oxidation. Here, we need to lessen the silver concentration. What will do that? Reduction. So, what is going to happen here is that the electrode, sorry about that, the silver electrode will become more of the ion, giving then electrons to then complete the reduction here. Now, whenever you create what is called a concentration cell is created when you have two solutions in contact and both of those solutions have the same ingredients that could respond as oxidation or reduction. When there's a difference in concentration, it causes a hill for the electrons to flow down. They will keep moving electrons until the concentrations are about equal. This doesn't yield that high of an EMF, but it does give us some voltage. So it's an interesting kind of battery to set up. The next example that I have for you to look at on that same page is asking you to determine the direction of electron flow. Oops, I'm not doing a good job with my directional notes. Very sorry. Determine the direction of electron flow and designate the anode and the cathode. If we would have a 0.010 molar iron plus 2 and 0.100 molar iron plus 2. Well, from the previous example, for these two equalized concentration, we would expect that this concentration of iron will decrease and this concentration of iron will increase. So thereby, this must experience the oxidation. So, the situation that we'll have, this will be our anode, the lower concentration, where the electrode will free electrons, giving more ion to increase this concentration. Here, this will decrease concentration because the ion will be pulling for electrons, depositing as neutral elemental iron. This will flow until the concentrations are about equal. Well, what else might we see if we're not at standard state? Can we revisit an equation that we've seen before? Remember from the last chapter that whenever we were not at standard state, we could predict spontaneity and calculate delta G at the new conditions by comparing to the standard delta G. And that would be adjusted by a factor of RT. Remember that R was 8.314 joule per Kelvin mole, times our temperature in Kelvin, times the natural log of Q, because we weren't sure if we were at equilibrium or not. Probably not, because then it would become K, and delta G would be 0. Well, we know that delta G equals negative ENF. So, if we say that not at standard state would be negative NFE, and standard state would be negative NFE naught, and then substitute in to this equation, we then get this. Well, let's simplify this. What if we divide each of our factors by negative NF? Well, then we would have E equals E naught minus RT over NF ln of Q. R, we know, is this 8.314. Your book beautifully shows that if we take into account what a natural log involves, take into account what R is, then we can actually create this form of the equation where E equals E naught minus 0.0591 divided by N log of Q. Log of Q.